In this lesson, we're going to talk about hierarchies and space transformations. So in Leadwerks, we can attach one entity to another. We can do this with the entity set parent command. And this will parent one entity to another so that when the parent moves, the child will move with it relative and maintain its position and rotation relative to the parent. And it's easier for me to just show you an example. So I'm going to copy the example here from the written tutorial, and I will paste this into the main.lua file. So here I'm showing you an assembly of different objects. We have this arm that's spinning around. This is the parent. And then we have the ship as a child of that, and so the ship is staying in the same place relative to the parent. And then in addition to that, I've added a box that's kind of stretched out on the front of the ship, and it's spinning around like a propeller, but it's spinning relative to the parent, which is the ship. So that's a fairly complex assembly. Let's see how I made it. So the stand, that's just the piece in the middle, and that doesn't really do anything. It's just there for visuals. The arm is the long box that was spinning around. And let's see, that's 8 units by 0.25 by 0.25. So that's why it's kind of long and skinny. And then we load this ship model from the documentation, and we call ship set parent arm. And importantly, we set the ship's position before doing that. And then that way, when we call set parent, it will maintain that same position that it was at. Okay, and then for the propeller, we're just creating another box, and this is 2 units, so it's pretty wide by 0.25 high and 0.1 deep. So it's like kind of a long and skinny object. And we're positioning it, we're moving it forward 1.25 units. And then we're calling set parent to the ship, but most importantly, we're supplying a second parameter here. By default, this parameter is set to true if you don't specify it. And if it's set to true, then the child object will maintain its global position when it is parented to the parent. If it's set to false, however, it will maintain its local position. So whatever its position is at the time this is called, it will maintain that. This will be its position relative to the parent, to the ship. And then all we're doing is the arm is turning 1 degree every frame. The propeller is turning 10 degrees every frame on its z-axis. And because it's parented to the ship, that just makes it spin around on the z-axis relative to the ship. So let's take one more look at that. There's the arm object. This is the parent. This is spinning around at 1 degree every frame. And then the ship was parented to the arm. And then this propeller was parented to the ship. And the propeller is rotating on its z-axis. And because it's parented to the ship, it keeps spinning relative to the direction that the ship is facing. So that's how we can make machines and just complex assemblies of objects, things that move together, is with parenting, and that's a hierarchy. Now, if you want to access the children that an entity has, you can do that with the kids array. Let's see if we can do this right now. We'll say entity equals arm. And it only has the one child because it only has the ship parented to it, but we'll do this anyways. And we'll say for n equals 1 to entity kids, this is if you put this hashtag in front of an array in Lua, this will give you the length of the array. Then we're going to print out child and the index, and then we'll print out the name. And I'm not sure what the name is going to be, but we'll find out. It's just whatever is stored in the model file. Let's see what it said. Child 1, name, sketchfab model. Okay, that makes sense. It's right there. So that's how you can access all the children that an entity has. Now, space transformations are an idea that's related to this. You can transform points, normals, vectors, and other data between different coordinate spaces. And this is something this is a very important concept. So you have several different coordinate systems. You have world, or sometimes it's called global space. And this is coordinates relative to the world origin. So this is not any object, this is just the world itself. This is world space or global space. Then you have local space, and this is coordinates relative to an entity, to a specific entity. And then you also have parent space, and this is coordinates relative to the parent entity, relative to an entity's parent if it has one. Now, if the entity does not have a parent, then parent space and world space are the same thing. So we can transform points and normals and vectors from so that we can find out what they are relative to one object or relative to or where they are in the whole world. So the most common way you're going to use that is with the transform point function. And this will convert a point in 3D space from one entity's coordinate system to another. And the way this is done is it accepts a position, a vec3, or you can specify you can specify x, y, and z separately. And then you specify two entities. And the first one will be the source, and the second one will be the destination. Now, if either of these is nil, then that means there's no entity, and that means it's relative to the world. So in other words, what this line of code is doing is it's taking the box position, and it's transforming it from world space, because nil is no entity, so it's just using world space. It's transforming the box's position from world space to the ship's space. So it will tell us what the box's position is relative to the ship. Let's see what that actually looks like. Okay, so the ship is pointing forward. It has no rotation, and it's positioned at the origin. And the box over here, it's on its right, and its relative position is 4, 0, 0. Okay? And yeah, that's where we set it initially. So because the ship has no rotation, and it's positioned at the origin, in this case, the ship's coordinate system and the world coordinate system are exactly the same. And so the boxes, when we transform the box's position from world space to the ship, it just remains the same as what we originally set it at, which is 4, 0, 0. However, if we hit the arrow keys and rotate the ship, now the box's relative position is changing. So I've got this, that's about as close as I can get it. So this first number is negative 8.10, and then it says e exponent to the negative 6. So that basically means it's really, really close to 0. And the second, the y position is 0, and the z position is just about 4. So we rotated the ship about 90 degrees to the right, very close to that. And now the box's position, when we call this transform point function right here, now it's returning something pretty close to 0, 0, 4 because the box is now in front of the ship. So relative to the ship, the box's position is 0, 0, 4. If I point the ship away, that's pretty close from the box. The box hasn't moved, but now when I transform the box's position from world space to the ship space, it has moved relative to the ship because the ship actually moved. So the position is now x is pretty close to 0, y is still 0, and the z position relative to the ship is pretty close to -4. That's the transform point function. And you will use this a lot in games. This is extremely useful because you can find out where an object is relative to another object's orientation. We can also transform a vector. Let me copy this. And here what we're going to do is we're going to transform the vector from the vector 0, 0, 1 from nil to the ship. And that's going to act in a similar manner. Only one little thing we're going to do to change this up. The ship's scale is now set to 2. So we made the ship twice as big, and that means its coordinate system is going to be stretched out to be twice as big. And that means when we transform the vector from world space to the ship, then that vector, the resulting vector in the ship space, it's going to be half as big. I'll show you. So the ship is now twice as big, and when we transform the vector 0, 0, 1 from world space to the ship, the resulting vector is 0, 0, 0.5. Whoa. Now if we move let's turn the ship 90 degrees to the right. And now you can see that's about as close as I can get it. But now that vector, this vector going into the screen, relative to the ship, now the x value is pretty close to -0.5. The y value is 0, and the z value is pretty close to 0. So relative to the ship, that vector has moved. It's now pointing in a different direction. It's pointing to the left of the ship, but it's also gotten smaller because the ship is scaled to be bigger. So that vector relative to the ship is a smaller number. Now if we use transform normal instead, all this does is it transforms a vector and then it normalizes the result. Because sometimes we want the normal and sometimes we don't care about the magnitude of the vector. And so when we use this, this will give us a normalized vector. You see, even though the ship is scaled, the returned vector is still 0, 0, 1. And here it's -1, 0, and then a number so close that it's practically 0. A number so small. So that's the difference between transform normal and transform vector. We also have some other transformations. We can call transform rotation, and you can transform a rotation. You can transform a quaternion between coordinate systems. You can use Euler angles, but as we've seen, quaternions are more accurate. So if you can, you'll usually want to use those. You can transform an axis-aligned bounding box from one space to another, and it'll give you another axis-aligned bounding box. You can even transform a plane from one coordinate system to another. So The most important one that you're going to use is transforming a point. Sometimes you'll use transform normal. And parenting objects, that's something you're very likely to use quite a lot. So if you have any questions, let us know. We're here to help. And I'll see you in the next lesson.